So we've had a look at developing neural networks using TensorFlow sort of lower level APIs, where instead of really thinking about neurons or units, you're thinking more about tensors and matrices and multiplying them together directly. And that's a very efficient way of doing it, but it's not really intuitive. It can be a little bit confusing, especially when you're starting to try to implement a neural network in those terms. Fortunately, there's a higher level API called Keras that's now built into TensorFlow. It used to be a separate product that was on top of TensorFlow, but as of TensorFlow 1.9, it's actually been incorporated into TensorFlow itself as an alternative higher level API that you can use. And it's really nice because it's really purpose-built for deep learning. So all of the code is very much built around the concept of artificial neural networks, and it makes it very easy to construct the layers of your neural network and wire them together and use different optimization functions on them. It's a lot less code and a lot less things that can go wrong as a result. Another benefit of Keras, in addition to its ease of use, is its integration with the scikit-learn library. So if you're used to doing machine learning in Python, you've probably used scikit-learn a lot, and using Keras, you can actually integrate your deep neural networks with scikit-learn. And you might have noticed in our previous lecture that we kind of glossed over the problem of actually doing train, test, or cross-validation on our neural network because it would have been a kind of a big pain in the butt. But with scikit-learn, it's very easy to do cross-validation and perform proper analysis and evaluation of this neural network. So that makes it easier to evaluate what we're doing and to integrate it with other models or even chain a neural network with other deep learning or machine learning techniques. There's also a lot less to think about, and that means that you can often get better results without even trying. With TensorFlow, you have to think about every little detail at a linear algebra level of how these neural networks are constructed because it doesn't really natively support neural networks out of the box. You have to figure out, how do I multiply all the weights together? How do I add in the bias terms? How do I apply an optimizer to it? How do I define a loss function? Things like that, whereas Keras can take care of a lot of those details for you. So when there's less things for you to screw up and more things that Keras can take on for you in terms of optimizing things for what you're really trying to do, often you can get better results without doing as much work, which is great. And why is that important? Well, the faster you can experiment and prototype things, the better your results will be. So if it's that much easier for you to try different layers in your neural network, different topologies, different optimizers, different variations, it's going to be that much easier and quicker for you to converge on the optimal kind of neural network for the problem you're trying to solve. Whereas if TensorFlow is putting up a bunch of roadblocks for you along the way, at the end of the day, you only have so much time to devote to these problems, right? So the more time you can spend on the topology and tuning of your neural network and the less on the implementation of it, the better your results will be at the end of the day. Now, you might find that Keras is ultimately a prototyping tool for you. It's not as fast as just going straight to TensorFlow. So sometimes you want to converge on the topology you want and then go back and implement that at the TensorFlow layer. But again, just that ease of prototyping alone is well worth it. Makes life a whole lot easier. So let's take a closer look. And again, Keras is just a layer on top of TensorFlow that makes deep learning a lot easier. All we need to do is start off by importing the stuff that we need. So we're going to import the Keras library and some specific modules from it. We have the MNIST dataset here that we're going to experiment with, the sequential model, which is a very quick way of assembling the layers of a neural network. We're going to import the dense and dropout layers as well, so we can actually add some new things onto this neural network to make it even better and prevent overfitting. And we will import the RMS prop optimizer, which is what we're going to use for our gradient descent. Shift-Enter, and you can see we've already loaded up Keras just by importing those things. It's using TensorFlow as a backend. Let's go ahead and load up the MNIST dataset that we used in the previous example. Keras' version is a little bit different. It actually has 60,000 training samples as opposed to 55,000. Still 10,000 test samples. And that's just a one-line operation. All right, so now we need to, as before, convert this to the shape that TensorFlow expects under the hood. So we're going to reshape the training images to be 60,000 by 784. Again, we're going to still treat these as 1D images. We're going to flatten these all out into 1D rows of 784 pixels for each 28 by 28 image. We also have our test data set of 10,000 images, each with 784 pixels apiece. And we will explicitly cast the images as floating point 32-bit values, and that's just to make the libraries a little bit happier. Furthermore, we're going to normalize these things by 255. So the image data here is actually 8-bit at the source. So it's 0 to 255. So to convert that to 0 to 1, what we're doing basically here is converting it to a floating point number first, from that 0 to 255 integer, and then dividing it by 255 to rescale that input data to 0 to 1. We've talked before about the importance of normalizing your input data, and that's all we're doing here. We're just taking data that started off as 8-bit 0 to 255 data and converting that to 32-bit floating point values between 0 and 1. That's all that's going on there. As before, we will convert our labels to one hot format. So that's what toCategorical does for you. It just converts the label data on both the training and the test data set to one hot 0 to 10 values. Let's go ahead and run that previous block there before we forget. And we will run this as well. Again, I'm just hitting Shift-Enter after selecting the appropriate blocks of code here. All right, as before, let's visualize some of the data just to make sure that it loaded up successfully. This is pretty much the same as the previous example. We're just going to look at our input data for sample number 1, 2, 3, 4. And we can see that our one hot label here is showing 1 in position 4. And since we start counting at 0, 0, 1, 2, 3, that indicates label 3. Using argmax, that gives us back the human readable label. And by reshaping that 768 pixel array into a 2D shape, we can see that this is somebody's attempt at drawing the number 3. Okay, so far so good. Our data looks like it makes sense and was loaded correctly. Now, you remember back in when we were dealing with TensorFlow, we had to do a whole bunch of work to set up our neural network. Well, look at how much easier it is with Keras. All we need to do is say that we're setting up a model, a sequential model, and that means that we can add individual layers to our neural network, one layer at a time, sequentially, if you will. So we will start off by adding a dense layer of 512 neurons with an input shape of 784 neurons. So this is basically our first layer that takes our 784 input signals from each image, one for each pixel, and feeds it into a hidden layer of 512 neurons. And those neurons will have the ReLU activation function associated with them. So with one line of code, we've done a whole lot of work that we had to do in TensorFlow before. And then on top of that, we'll put a softmax activation function on top of it to a final layer of 10, which will map to our final classification of what number this represents from 0 to 9. Okay, so wasn't that easy. We can even ask Keras to give us back a summary of what we set up just to make sure that things look the way that we expected. And sure enough, we have two layers here. One that has 512 and then going to a 10 neuron layer for the final classification. And this does sort of omit the input layer, but we do have that input shape of 784 features going into that first layer. All right. Now, you also might remember that it was kind of a pain in the butt to get the optimization and loss function set up in TensorFlow. Again, that's a one-liner in Keras. All we have to do is say that our loss function is categorical cross entropy, and it will know what to do there. We're going to use the RMS prop optimizer. Just for fun, we could use any other one that we wanted to. We could just use Atom if we wanted to, or there are other choices like AdaGrad, SGD. You can read up on those at this link here if you want to. And we will measure the accuracy as we go along. So that's all that's saying. Let's go ahead and hit that, and that will build the underlying graph that we want to run in TensorFlow. All right, so now we actually have to run it. And again, that's just one line of code with Keras. All we need to do is say that we're going to fit this model using this training data set. These are the input features, the input layers that we're going to train with. We want to use batch sizes of 100. We're going to run that 10 times. I'm going to set a verbosity level of 2 because that's what works best with an IPython notebook. And for validation, we will provide the test data set as well. So instead of writing this big function that does this iteration of learning by hand like we did in TensorFlow, Keras does it all for us. So let's go ahead and hit Shift-Enter and kick that off as well. Now, Keras is slower than TensorFlow, and it's doing a little bit more work under the hood, so this will take more time. But you'll see that the results are really good. I mean, even on that first iteration, we've already matched the accuracy that we got after 2,000 iterations in our hand-coded TensorFlow implementation. We're already up to epoch 6, and we're approaching 99% accuracy on our training data. Keep in mind, this is measuring the accuracy on the training data set. And we're almost there. But yeah, I mean, even with just 10 epochs, we've done a lot better than using TensorFlow. And again, Keras is kind of doing a lot of the right things for you automatically without making you even think about it. That's the power of Keras. Even though it's slower, it might give you better results in less time at the end of the day. Now, here's something that we couldn't really do easily with TensorFlow. It's possible. I just didn't get into it because that lecture was long enough as it was. But remember that we can actually integrate Keras with scikit-learn. So we can just say model.evaluate, and that's just like a scikit-learn model as far as Python's concerned, and actually measure, based on our test data set, what the accuracy is. And using the test data set as a benchmark, it had a 98% success rate in correctly classifying those images. So that's not bad. Now, mind you, a lot of research goes into optimizing this MNIST dataset problem, and 98% is not really considered a good result. Like I said, later in the course, we'll talk about some better approaches that we can use. But hey, that's a lot better than we got in the previous lecture, isn't it? As before, let's go ahead and take a look at some of the ones that it got wrong, just to get a feel of where it has trouble, things that our neural network has challenges. The code here is similar. We're just going to go through the first 1,000 test images here, and since it does have a much higher accuracy rate, we have to go deeper into that test data to find examples of things that went wrong. We'll reshape each image into a flat 784 pixel array, which is what our neural network expects as input. Call Rmax on the resulting classification in one hot format and see if that predicted classification matches the actual label for that data. If not, print it out. All right, so you can see here that this model really is doing better. The ones that it's getting wrong are pretty wonky, okay? So in this case, we predicted that this was a number 9, and if I were to look at that myself, I might guess that was a 9 as well. Turns out this person was trying to draw the number 4, but this is a case where even a human brain is starting to run into trouble as to what this person was actually trying to write. I don't know what that's supposed to be. Apparently they were trying to draw the number 4. Our best guess was the number 6. Not unreasonable given the shape of things. Here's somebody who was trying to draw a 2, but it looks a whole lot more like a 7. Again, I wouldn't be too sure about that myself. So, even though we flattened this data to one dimension, this neural network that we've constructed is already rivaling the human brain in terms of doing handwriting recognition on these numbers. I mean, that's kind of amazing. That one, I probably would have guessed a 3 on that one. But again, you can see that the quality of the stuff that it has trouble with is really sketchy. What is that? A scorpion? Apparently that was supposed to be an 8, and our best guess was a 2. But that's smudge. Wow. Okay, yeah, some people really can't write. That's a 7? Yeah, I mean, you get the point here. So just by using Keras alone, we've gotten better accuracy, we've gotten a better result because there's less for us to think about. All right, and you can probably improve on this even more. So again, as before with TensorFlow, I want you to go back and see if you can actually improve on these results. Try using a different optimizer than RMSprop. Try, different topologies. And the beauty with Keras is that it's a lot easier to try those different topologies now, right? Keras actually comes in its documentation with an example of using MNIST, and this is the actual topology that they use in their example. So go back and give that a try. See if it's actually any better or not. See if you can improve upon things. One thing you can see here is that they're actually adding dropout layers to prevent overfitting. So it's very easy to add those sorts of features here. Basically what we've done here is add that same dense layer of 512 hidden neurons, taking the 784 features, and then we're going to drop out 20% of the neurons at the next layer to force the learning to be spread out more and prevent overfitting. So might be interesting to see if that actually improves your results on the test data set by adding those dropout layers. All right, so go play with that. When we come back, we'll do some even more interesting stuff using Keras.